Hello. So, in the previous discussion, we looked at the ordinary black bolts. So, now let's look at the high strength friction grip bolts. And these come in two forms. We have the parallel shank and the wasted shank friction grip bolts. This is an example of the parallel shank bolt. And this is how we have the connection. So, here they are called friction grip bolts because the reliance of the connected parts depends on the ability of them to grip to each other firmly, that is, without any slip. Okay, so we rely on the tensile strength of the bolts in gripping the two surfaces, these two plates together. So what it means is that all connections using this are checked for slip resistance. That is for us to be sure that we don't have the the connection failing by slipping. So the bolts are normally, you know, they are normally added with what steel washers to prevent damage to the connected parts. And because we are emphasizing the fact that the efficiency depends on the friction resistance between the surface. We try to ensure that they do not have what maybe rust, paint, or grease that would reduce the coefficient of friction between the surfaces. So, and also those that we designed to be non-slip, we also try to check for the bearing capacity of the connected parts and also the shear capacity of the bolts. So slip resistance. So those bolts that we designed to have slip resistance. That is to be non-slip in service. This is how we estimate the slip resistance. Okay, so we have this expression where Ks is equal to 1. That's the coefficient for bolts in standard clearance holes. And the slip factor. So the slip factor actually varies depending on the surface conditions. So, and the slip resistance is given in table 35 of the code. So where we have uh, grid blasted surfaces, we have 0.5, where brushed 0.3, where the surfaces are not treated, we have 0.2. So for friction grip bolts designed to be non-slip under factored loads, this is the expression. You see that we are looking at the same formula, just that the coefficient here is changed to what 0.9. And the P naught in the two formulas is the minimum shank tension. That is of the bolts. So as we said, after checking the slip resistance, we also try to check for the bearing and shear. So the bearing capacity of the connected parts is given by this expression. It's very similar to the first one we saw. That is the one we saw in the ordinary bolted connections. So here we have dB, that is the diameter of the bolts, the thickness of the plates, the bearing capacity of the connected parts. So the same apply here. So here E is your end or edge distance. So regarding to shear, the shear capacity of the connected connection is the same as with the ordinary bolted connections, PSAS. Okay, where PS is the shear strength of the bolt and AS is the shear area, normally given as the tensile area of the bolt. So in the same manner, where we have a combination of shear and tension, apart from checking shear and tension separately, we would have to ensure that this expression is satisfied. Okay, where Fs is the applied shear force, and this F total applied tension in the bolts. Then PSL is the slip resistance that we computed. Then your P naught is the minimum shank tension. So all this should be less than or equal to 1. So the next to look at is block shear. So this can occur in a beam column connection. So this is the side of the beam. So this occurs, you can have shear failure, at the row of bolts, okay, that are in the direction to the applied force or the stress. So this would accompany by what? Uh, tensile rupture along the stress, where we have the stress happening, and then we can have rupture perpendicular, so perpendicular to this. So this would result in the material being torn apart. Okay, so you can have a whole section of this depending on the intensity of the load. You know, you can have section of the your beam being torn apart. Okay, so that is a well-put beam. You can have it being torn apart. And of course, our task is to be able to avoid that. So to avoid that, we use this expression to ensure that the applied shear force does not exceed that force. So we have the parameters Py, that's the design strength, and T is the thickness, and you have Lv. So Lv is that dimension or that distance in direction of the stress or the applied force. And we have Lt, perpendicular to that direction. We have Ke, we saw it, that's the effective net area coefficient. So we have various values given in the code. We have K K depends on the number of line of bolts. So where we have single line of bolts, we have 0.5. Where we have double line of bolts, we have 2.5. So once we have all these parameters, we insert them, we compute, we check the block shear force, and we check to ensure that the applied shear force does not exceed that force, and our connection will be safe.